a water surface that I filmed. This is near the river. This is at the River Rhine, actually, in Germany. And so what you notice, and you've seen it all before, you see that there's some upwelling or what we call boils. And these boils can be of the so-called first, second, or third kind, and they occur over rough beds. And generally, first kind is sort of bathymetry, topography generated boils. Second kind is secondary currents, and third kind is sort of all background turbulence. So that's basically the small scale stuff. And we're interested in the momentum balance. We want to calculate or quantify how the surface deformations contribute to the momentum balance. We know that there's processes taking place at the air-water interface. And so one of the underlying key questions here is why and how does the water surface deform? Obviously, there's a lot of work that has been done in this regard, and so hopefully with our simulations we can provide some novel insights. The method that I'm talking about is large eddy simulation. This is stuff that we've been doing for a while now. This is an in-house code that we're applying. So it's not a black box. And we try and keep it state of the art, and we've introduced or included the level set method. And the level set method is an algorithm that can solve for the air-water interface and how that air-water interface moves. I've written a vision paper on large eddy simulations, and I hope some of you are familiar with the method. So here I want to talk about a few cases that we've looked at recently. Case number one here would be the free surface flow over a backward facing step. Why have we chosen a backward facing step? Well, it's a well-known flow. It's a well-known it's an easy geometry, but it gives us almost all the fluid mechanical properties or complexities that we're looking for. Then there was some work on it from Professor Nesu's group, and we've got some data of that. And so that was good because we could validate our simulations. Here in the lower half of this slide, you can see some of the profiles. There's a recirculation, so that there's a separating streamline, phi equals 0. There's a recirculation behind the step. And then there's a boundary layer and a shear layer and a boundary layer on the downstream side. So our validations show that the simulation does a good job in reproducing the flow. And then we looked at some of the properties here of backward facing step flows, and this is free surface. So just so you know, this is an open surface, so everything that's white here is air, and everything below that line is water. And we've looked at 3 different cases. One we refer to as the deep case, a medium case, and a shallow case. And the changes here in terms of water surface are quite subtle, but if you look closely on the very shallow flow, the water surface rises on the downstream side because it's a
Austin, sorry to interrupt. I don't know if this is the case for everybody. Yeah, my video stalled. I don't know if that was the case for everybody else. Okay.
I think it had. Yeah, I'm seeing a slide, turbulent kinetic energy, with 3 graphics, grayscale graphics now.
Yeah, maybe there's a bit of a delay in when we change over the slides. Yeah. So sorry. Starting again from that slide, if you see the TKE contours now. So we've looked at 3 cases: LES2, LES3, LES4, the different water depth. The white bit above the gray is sort of is air, and then the dotted line or the line here indicates a water surface. And on the very shallow case, you can see that the water surface rises on the downstream side of the step. And you can also see the shear layers here that are visible, and it's clearly its strongest in the most shallow case in LES4, and so there's quite a bit of turbulence going on above that separating streamline. So in this slide, we can see some of the shear layer turbulence. These are isosurfaces of the Q criterion. So they visualize turbulent structures, coherent flow structures, and in the background you can see contours of the vorticity. And the difference in terms of the amount of turbulence between LES2 and LES3 is not very big. It's all concentrated near the step. But if you look at the most shallow case, you can see the most turbulence, and you can also kind of see on the in this area here that there is some interference with the water surface. Having a look at this in a little bit more detail, is you can see again this vorticity plot. So areas of high vorticity are red. So there's this shear layer. It also is unsteady in time. And if we look at the turbulent structures here that are associated with it, you can kind of see close to the step. This is sort of a roller, as it's called, and then that roller is basically comes from the roll up of the shear layer. Some of the vortices are already starting to move towards the water surface before reattachment, but some of the turbulence, as you see, this big Kolk Boyle vortex, as it's called, has started to rise up a little bit further from the downstream and near the reattachment zone, and we've quantified this. And we've also looked at how the water surface responds to this turbulence. In the deep case, which is the top left here, you can see a bit of waviness that also stems more from the inflow into the channel than from the turbulent structures themselves. On this side here, we also see the waviness, but further on the downstream side, we also see some water surface deformations in the form of boils. And when I show you this one from the LES4, which is the shallowest case, we can kind of see the waviness as well. But then here on the downstream of the reattachment zone, we can see clearly upwelling. We can see some stronger deformations, and especially in the form of these rollers or these hairpins that are reaching the water surface and then deform it accordingly. So here, this is just to show you the water surface rise. This is the mean, the average rise of the water surface. We've also got the measurements here. And the shallowest case, so depending on the depth, obviously the deepest case, it doesn't rise too much, the water surface of it. And then the shallow one rises more in a more pronounced way. And when we look at the surface fluctuations, we can clearly again see the LES4, the shallowest case, has the highest RMS. And so we continue to investigate that case. But what's really interesting is how it deforms and what causes the deformation. And here we are looking at 2-point correlations. And we can see here from this is the medium depth case. We can see here the dividing stream. This seemed to be sort of a time delay. So here are the three cases it's a medium depth case, it's a dividing streamline, and it's 2-point correlation. And so the reference point is always near the this black dot here. So this is where the reference point is, and then we can see that the turbulence or the fluctuations seem to be correlated all the way to the water surface. If we put the reference point close to the step, the correlation starts to drop fairly quickly. Further downstream, relatively strong correlation, and again we can see some correlation near the water surface. And for the one where we know that the so-called cold boil vortex occurs, we can see some reasonably strong correlation over a wider area, and again it reaches the water surface. Case number 2 that we're looking at the moment is the free surface flow over longitudinal strips. So in case 1, we've seen more the cold boils of the first kind. So in this case, we're interested in the cold boils of the second kind, so the ones that are generated by secondary currents. So here we've done a simulation that is sort of analog to some experiments from the University of Aberdeen, and this is a fairly long domain. We know that these very large scale structures of motion extend over a wide area or in the streamwise direction, so we had to go with a very long domain. At the bottom here you can kind of see these blue triangles. These are the strips. And you can kind of see the you know, intermittent high and low velocities on the water surface. Then we've done some 2-point correlations again to identify these secondary currents. We are interested in the effect of the water depth. So how does the water surface response change when the flow is more shallow? Or shallower, and you can see the secondary currents. So this one is positively correlated, and then because the structure is basically a mirror image on the other side of the strip, it's negatively correlated. And we've done comparisons with experiments, and this looks quite reasonable. And so we then looked at the water surface texture or deformation, and you can see here, I hope it's kind of clear that along or over the strips, you can sort of see these boils, and in between the strips, you know, the water surface is relatively calm. So a train of boils over the strips, and not so much deformation inside this or in between the strips. And when we look at the root mean square of the free surface elevations, then you or the normalized, then you can kind of see the water surface deformations or the fluctuation of it is stronger over the strips, and certainly not as strong in the troughs. And then we looked at the texture and compared the difference between deep and shallow flow, and you can see here that, you know, again, this is obviously exaggerated. We've you know, stretched it in the vertical so that you can see it a little bit clearer. And from this picture, it only gives you a qualitative impression, but again, you can see the train of boils above the strips and less so in between. In comparing the two, you can see that the amount of deformation is similar. And when we look at this image here, then we can say that the red line, which is the shallow case, and the blue line, if you look at the absolute water surface fluctuation, it's kind of similar. It has a similar magnitude. Okay, 1 minute. I'll hurry up. Similar magnitude, but obviously the shallow one seems to be fluctuating a little bit more. And when we look at the RMS, so sort of you can see that especially in the lower half here of this image, you can kind of see that the deeper RMS fluctuations is a bit smoother, and the shallow one is a bit more pointy, but the magnitudes are kind of similar. So the last thing I wanted to show you is this abutment flow. Again, we have a bridge abutment, and we have deformations, and we have turbulent structures that are causing the deformation. And wherever we have a vortex, we have a depression, and this is the visualization of this vortex beyond the bridge, past the bridge abutment. And yeah, and this is work that we've done with my colleague Terry Stern at Georgia Tech. So sorry, this is all a bit rushed, but take-home messages here. Water surface deforms due to bathymetry and turbulence. We know, and we've sort of quantified that the deformations reflect what's underneath. We know that the boils of the first and second kind are the most noticeable, and our eddy resolving method seems to be a good tool, but we always stress that it only works in combination with experiments, because that can be used or should be used to validate the simulations first. Thank you for your attention, and I'm happy to answer any questions. Sorry, Rob, I ran over.
It's okay. Thanks, Torsten. So we have time for a quick question if anybody has anything that they've come up with.
Yeah, I can ask a question. It's Alex Oet from France. I don't know if it's very in the scope, but it seems that you can generate some very realistic images of the free surface, showing the roughness of the turbulence and everything. Do you think that if you can generate like a sequence like you show at the end, it could be also a way to validate or to check the capabilities of some surface velocity method, like you generate kind of videos showing some roughness of the surface, and you know everything because it's numerical simulation, and then we apply our method and we see if it's working well or not. So it's not, I know that it's not the topic of your research, but it's maybe another application.
Yeah, absolutely, and I'd be happy to say that these simulations could be used in turn to validate experimental methods. We use experiments to validate our simulations, but we could also then, once we have confidence in our tool and in our results, we could use it again to validate some LSPIV or some other software. It's more of a verification really than a validation, I suppose. Yeah. Thank you for the question.
I'll just draw your attention, Torsten, to a comment by Todd Cohen, which is that his group has LSPIV and ADV measurements in a wide open channel of forced secondary flows, if you're interested. So perhaps that could be a link that you guys could explore after this.
Yeah, definitely.
Workshop.
Yeah, happy to work together.